Alright, so we don't have any homework to check, so let's just go right into our notes. So, notes today. I'm going to warn you guys, this is probably one of my least favorite days of this unit and of the semester, probably. A lot of the stuff we talked about and actually do today probably won't be on the test. I will make sure that the stuff that will be on the test, I will highlight for you. I'll let you know, hey, these are things you need to know. But we're going to graph things today. We're never going to ask you to graph graph an exponential on the test. Alright? And we'll talk about that as we go along. Like I said, it's one of my least favorite days, so let's just kind of power through it. We're good to go. First things first, exponential growth functions. We talked about exponential growth. We talked about it last unit, right? We did y equals a times 1 plus r to the t power. You guys remember that? Right? Same thing, y equals a times b to the x power. B has to be greater than 1 for it to be growth. That's why we did 1 plus r. So if we had a rate and we added it to 1, we knew it would be greater than 1. So we know our exponential growth is y equals a times b to the x, and b is greater than 1. Those are important to know. That you'll need to know for your tests, for your homework, things like that. When b is greater than 1, exponential growth will happen. And we'll talk more about that later on today. But that is something really important. So I highlighted, circle. I think you guys wrote it down even. The other thing you need to notice from this slide that's really important. From left to right, which way does my graph go? Up or down? Up, right? If I look at it from left to right, it's going up. Exponential growth will always go up from left to right. Okay, so we'll always go up from left to right. Now, if we do a little experiment here, we look at our graphing calculators, we graph three functions. Those of you that don't have a graphing calculator today, I'll do it on the board as well. So if I look in here, y equals 2x. This is just the one I'm starting with. I should get a graph that looks like that, right? So y equals, oh, sorry, I skipped that. If I go to y equals, if it'll let me, I hit 2 caret key, and then x is this button right here next to alpha. It's got x, t, theta, n. That is your variable button. So if you're ever trying to put a variable in, you hit that button. Well, there we go. So you should hit y equals 2 to the x, and if you hit graph, button in the top right, it'll graph that equation for you. Now, hopefully you can all see it and it looks like mine. When you graph yours. Yes, does it look like mine?
Wait, what do you do?
Graph. Now, like I said, we're going to draw them on there right now, but we're not going to ask you to draw anything on a test. We may ask you to match an equation with its graph, but at that point I'd probably look at, well, where does it cross the y-axis? How quickly does it go up? Things like that. So, if I look here, I'm going to draw it, y equals 2 to the x. Where does it cross the y-axis? So what number? 1. Right? So when I draw it, I can notice it's getting really close to the x-axis. Do you think it'll ever cross the x-axis?
Going down.
On this side over here? Never does. So if you're drawing a graph, or you see a graph that crosses the x-axis, it's not exponential. So if we're looking at it, draw it really close. I know it's crossing at 1, then it's going upwards very steeply. Now, does it have to be perfect? No. It's an estimate. Right now we're doing a sketch of a graph. Like I said, we'll never have you graph on the test. The second one, we want to see what happens when our value in front changes. So here it was actually like times 1. Right? It was imaginary. Here I have times 3. Let's see what changes. So when I do change from 1 to 3, I'm going to make this one red. 3 times 2 to the x. And I graph it. Notice what happens to that red graph.
No.
What do you notice?
It goes to the third one on the y.
It what?
It goes to the third one on the y.
Third one on the y. It crosses the y-axis at 3. It's going up quicker. Right? So if I make bigger numbers, it's going to go up quicker. It's going to cross that y-axis at a different point. So if I go to draw it, same thing. I cross at 3 and it goes up. Like I said, we'll never make you graph these on tests. You might have to, like on the homework tonight, you have to match graphs with their equations, but you're never going to have to draw them. So if the bigger the number, it went up quicker and it went up to a higher number, what do you think is going to happen if I use a smaller number like 0.5? What?
It'll take longer.
It'll take longer, right? Well, let's double check that. Y equals 0.5 times 2 to the x. So let's see, the black graph, it does take longer, right? It crosses at 0.5 instead of 1. So it takes longer. If I draw it on here, 0.5, and then it goes up. Like I said, we're just sketching. The big thing to know here, guys, is notice when it changes in front, our graphs are going to change.
Wait.
Is there a way that you could look at, let's say, this second equation here, and tell me, without looking at a graph, or without plugging in your calculator, if it was exponential growth or not?
Yeah.
How?
Because the first number's been larger than 1.
Not the first number,
the
but
second number.
the number with the x value is greater than 1. We just said that. You need to know how to do that. You need to be able to look at an equation and tell me, is it exponential growth or is it exponential decay? We'll talk about what makes it decay in a second. But because this is greater than 1, I know this is going to be growth without even graphing it. Okay? Any questions so far? Like I said, you don't need to worry about being able to graph on the test. You might need to match things with graphs. You might need to be able to tell its growth by looking at the graph, because it goes up from left to right, but you won't have to graph them. Okay? Any questions? Yes, sir.
So it's just the 2x and left with 0.
So what does the 2 mean?
Yeah.
So that's technically our rate. So it's growing at a rate of 200% now.
Okay.
Or actually technically 100%. It's 1 plus 1 then. So that's just our number, or how quickly it's growing. Okay? All right. Then, let's look at an example again. I'm not going to graph it. I'll just graph it. If we look at y equals 5 times 2 to the x, if I drew that graph, it would cross my y-axis at 5, and it would go up even steeper than the ones that we've seen so far. Right? So if I drew it, it would go up and cross at 5, and be even steeper than the ones we did before, because it's a bigger number. It goes up even quicker than normal. So where does it cross the y-axis? I just gave that away. At 5. 0, 5, or y equals 5. What do you notice about the domain of this graph, or the x values of the function? Is there any limit to what x value I could have here? Or is there any spot where my graph will not go as an x value? If it keeps going on and on forever, will it reach 100 for my x values? Will it keep going farther and farther to the right? What do you think?
Yeah.
Yeah, right? This arrow tells me it's going to keep going on and on forever. It's going to hit all those x values. What about the negative x values? Will it keep going to all the negative x values? Yeah. So if I were to write the domain, which you won't have to do on a test either, we're kind of introducing it to you, it'd be all real numbers. What about the range, or the y values? If you look at this graph I just drew, and how we talked about before, are there any y values that we will never get to? What are they?
1, 2, 3, 4.
Never at 1.
Oh, they're right there.
Are there any y values that we're not going to hit? Negative. Right? We said it's never going to hit that x-axis. It'll never cross the x-axis. So if I were to write my range out, I would write that it gets really, really close to 0, but it never reaches it. So it'd be any values greater than 0, be any positive values. That's really important with exponentials, guys, because our graphs will never cross that x-axis. Ever. They'll never get to 0. Right? So we get really close to 0, but we never get there. And lastly, is there a horizontal line that doesn't cross? Yeah, we just talked about it. It's the x-axis, right? It's y equals 0. An asymptote, that's a really key vocabulary word. We won't have a vocab quiz, you don't need to worry about that. But you will see that like in FST, you will see that in pre-calc. An asymptote is a line that our graph will never cross. It's an invisible line. Like if you look on a graph here, is there technically any line here stopping our graph from going anywhere? No, but there's like an invisible line drawn in here that it will not cross. That's what we call an asymptote. It's a line that your graph will never touch. It'll get really, really close to it, but it will never touch it. All right? Okay, so big things we should remember so far. Exponential growth. From left to right, the graph goes up. And if I'm looking at the function, b is what?
Greater than 1.
Greater than 1. Those are the two huge things we need to know about growth. Decay. Exponential decay. Format for exponential decay is the exact same as it was for growth. Y equals a times b to the x. Now decay happens when b is between 0 and 1. So remember when we did our exponential decay functions, we did 1 minus r. That was because we needed to get it between 0 and 1. So we knew it was decay. So it's growth when b is greater than 1, decay when it's between 0 and 1. Now, I'm not going to make you graph these. They're technically already graphed for you. I just want to look at them and see. This is our first one, right? Y equals 1/2 x. Right? You're not going to be asked to graph on a test. I'm not going to worry about that. If I look at this, how can I tell just by looking at that function that it's decay?
It's going down from left to right.
It's going down from left to right. First of all, if I look at the graph, it's going down from left to right. That's huge. But what about the function? Y equals 1/2 x. Alex?
B is between 0 and 1.
B is between 0 and 1, right? My b value, the part that has the exponent, is 1/2. That's between 0 and 1, right? So it's decay. What if I looked at your next one? Y equals 1/4 to the x power. 1/4 is my b value. Is that between 0 and 1? Yeah, so it would be decay. What about if I looked at y equals 1/5 to the x power? My b value there is 1/5. Is that between 0 and 1? So would that be decay? Yeah. Right? What if we looked at one of those original ones? Y equals 3 times 2 to the x. What's my b value here?
6.
Not 6. 2, right? It's a part that has our variable. That's my b value. So would that be growth or decay? Growth. That's kind of the really important thing we need to know, guys. Be able to look at a function and tell us whether it's growth or decay just by looking at the b value. We also need to see, looking at a graph, if it goes down, it's decay. If it goes up, it's growth. That's the other big part of stuff we need to take away from today. Alright, those are the really two big takeaways from today. Someone tell me what the two big takeaways are. I just said them. I'm really glad you all are paying attention. I'll go over them one more time. Looking at a function. Being able to tell me whether it's growth or decay by looking at the b value. If it's greater than 1, it's going to be growth. If it's between 0 and 1, it's going to be decay. If I look at the graph and it goes down from left to right, it is going to be decay. And if it goes up from left to right, it's going to be growth. Alright. We have one application problem we're going to do and then we're done. Okay? Cool? Yes? No?
Cool.
Okay. Thank you all for responding.
You're welcome, Mr.
In 1999, wind turbines in Europe generated 5 gigawatt hours of energy. Over the next 15 years, the amount of energy increased by about 59% per year. Increase is telling me I have exponential what?
Growth.
Growth. So if you'll recall, our exponential growth formula is y equals a times 1 plus r to the t power. Right? We had that last unit. That was our formula. We're going to use that same formula to write a model giving the amount E in gigawatt hours of energy t years after 1999. Alright? So, I want to know the amount E of energy. So that's my Y value. So E equals. What is my A value? What's my initial amount of energy? 5 gigawatt hours, right? They generated 5 gigawatt hours. That's my initial amount. Times 1 plus. How much am I increasing by? What's my rate? 0.59. Right? 59%. And it's in T years after 1999. So just the T power. So I wrote my model. I'm good to go. That's step 1. All done. Step 2 asks, well, how much energy was generated in 2009 then? How could I figure that out? How many years after 1999 was 2009? 10. So where can I put 10? Put it in for time, right? Put it in for t. T equals 10. So I would do 5 times 1.59 to the 10th power. And I can plug that in my calculator. Yes, we've done this before. Yes, there's a new part to it in the next part. Just bear with me. To the nearest tenth, how many gigawatt hours were generated in 2009? Everyone should have put this in their calculator.
516.35.
Everybody got? 516 point what?
35.
So 4. We'll go to the 10th. 516.4. I know I'm switching up on you guys, but did we all get that when we put that in our calculator? Yes?
Yes.
Thank you. Alright, part C then. Estimate the year when 80 gigawatt hours of energy were generated. Am I going to plug 80 in for T? Is that a time? No. I'm going to plug it in for E, because it's the amount of energy that was generated. So 80 equals 5 times 1.59 to the T power. Right? All I do is I plug this into my equation. Now, how do we solve that? I want to solve for T. There are 2 ways we can go about solving this. The first way I'll show you can do by hand. The second way I'll show you is in your calculator. Alright? So, if I want to do this by hand, I have an exponential piece here. I need to isolate that. So I'm going to divide by 5 on both sides to get rid of that. I get 16 equals 1.59 to the T power. My exponential is all by itself. Well, how do we say we solved that then? When we're in exponential form, we're trying to solve. What do we need to do? We just did it in our bell ringer. What did we do once we got our exponential part isolated? Switch it to log form. Right? So if I do this, I put in log base 1.59 of 16 equals T. And I can plug that right into my calculator to figure out how much time it took to get 80 gigawatt hours of energy. If you need to do change of base, it's log of 16 divided by log of 1.59 to the nearest tenth of a year. That's X, I want T. What is T going to be? If you plug this log in your calculator, what is T going to equal?
5.98. If you round it.
5.98 or 6.0. Right? Alright. That is the first way to solve it. That's the way that we've been solving everything. And now we just put it into an application. The second way, you can use your calculators. You can use that cool graphing mode. But it's a little more difficult, it's a little more time consuming, I think. Alright? If you go into y equals, so go into y equals in your calculator. You plug in y equals 80. That's the left side of my equation. And y equals 5 times 1.59 to the x power, the right side of my equation. So I'll do that too, that way we can see it. Y equals, oops, excuse me, 80. Y equals 5 times 1.59 to the t or to the x, doesn't matter. Those should be the only 2 in there. If we graph it, and we find their intersection point, that'll tell us how many years it'll have to be. So if I graph Do you see an intersection point? Is there any part where two graphs will intersect on there? Because my window's not big enough. How many gigawatt hours did I want?
80.
80. If I look, guys, if you hit window, your window controls how big your graph is on your calculator. If I go from negative 10 to 10, will I ever see 80? No. So what I might do is my x's, and all those are years, I'm going to leave those at probably, I'm not going to go all the way to 80, I'm going to go, let's go with 0, look at that, 0 to, let's go 40 years. Doesn't matter. My y values, that was my gigawatt hours, so I'm going to go 0 to, I said I had to get all the way up to 80, right? My maximum had to be 80, so I'm going to go a little above that, so I'm going to say 100. Okay? Now, when I go to hit graph, do I have an intersection point? Yeah. Now to find that intersection point, you're going to need to hit second, trace, that didn't work, second, calculate, you want intersect, you want the fifth one down. You enter 1, 2, 3 times, and it'll tell us 6.0 or 5.9788 years. Right? That way, like I said, it's a lot more time consuming. There's a lot more steps you have to remember. I'd be more than happy to walk through it one more time if you'd like. Otherwise, you can just do it by hand how we've been solving them. Okay? Either way should get you the same exact answer. Does that make sense?
Yep.
Do you want me to walk through it one more time? I'll go through it quickly one more time, alright? First thing you need to do is in y equals, put in both sides of your equation. 80 and 5 times 1.59 to the x power. Second thing you do is you need to graph it. Change your window if you need to. Right? Make sure it's set big enough so you can see both the intersection points. Okay? Then you hit second, trace. The fifth one down is intersect. And you go 1, 2, 3 times with enter, and your x value is going to be how long it takes. 6.0 years. Okay? Either way should work, on the calculator or by hand. Any questions? What are the two big takeaways from today, from our notes? Anyone give me one of them? You got one?
Being able to tell the difference between growth and decay.
Being able to tell the difference between growth and decay, that involves both of them, right? By graph, growth goes which way if you look at it left to right?
Up.
Up. Decay goes which way if you look at it left to right?
Down.
Down. Good. That's one of the takeaways. Second takeaway, if I look at the functions, with growth, B is what?
Greater than 1.
Greater than 1. Decay is between
1 and 0.
0 and 1. Good. Those are the big things you need to know for the test.